Alright, last topic in this matrix algebra section. I'm going to go back to a system of equations now. We're going to use this matrix algebra to solve a system of equations. And this one hopefully looks familiar if you've been following through the videos. We solved this exact system using the elimination method. We solved it using Kramer's rule. And now we're going to look at it using matrix algebra, particularly the inverse matrix. What I want you to notice, well, first of all, we already know the solution from the other times that we've solved this system. So I just want you to have it here so we can verify that we got it correct after we're done. What I want you to notice is that there are some matrices kind of hiding in this system. One of them we've actually seen already when we did Kramer's rule. It's the matrix that contains just the 4 coefficients on the left side here. Okay, so we're going to call that matrix matrix A. All right, matrix A is the matrix, in this case 1, 3, 2, -3. Okay. There's another matrix, it's what we call a column matrix on the right hand side here with the 5 and the -8. We're going to call that one matrix B, and it's just the 5 and the -8. Okay, so far I have a 2 by 2 matrix, and here I have a 2 by 1, 2 row 1 column. There is one other matrix hidden in here, and you may not be able to tell where it is or what it is, but it's a matrix that contains the 2 variables, x and y. I'm going to call that matrix big X. Okay, that's typically the variable that we use for these variable matrices. Okay, matrix made of variables. And so that matrix is going to just be a column matrix also with little x, little y in it. And that also is a 2 by 1 matrix. Okay. Now what's interesting is that this original system is the product, the left side anyway, is the product of A and X. If you think about it, A times X is actually 1, 3, 2, -3 multiplied by xy. And when we do our rows times columns, first row, first column, you get 1 times x, 1x, 3 times y. And then if you do second row, first column, you get 2 times x and -3 times y. And you create exactly what's on the left side of the original system by doing this. Okay. Now it's interestingly it's equal. Now this is a new matrix, and it needs to be equal to the B matrix, right? It's equal to these 2 numbers here. So what's interesting is that the AX matrix together should equal the B matrix. Now in solving a system of equations, we're looking for the x and y values. We're looking to solve for this matrix. Now to do that, we're going to utilize this idea of inverse matrices. You might think, if this was just a linear equation, you might think you'd have to divide by A to get rid of the A and isolate the x. But in matrices, remember, we can't divide by a matrix. Instead, we multiply by its inverse. Okay, so A inverse A eliminates the A's, and it becomes I times X, the identity times X. And the identity times anything is just itself. Okay. However, on the right-hand side, the A inverse matrix must be multiplied to the right side in the same position. The reason for that is that matrix multiplication is not necessarily commutative. That means that if you multiply them in a different order, if you change the order, you may change the answer. So we have to, we call it left multiply. We multiply both of these on the left hand side, because if I did one on the left and one on the right, it might change the answer. So I've got to be very careful to be consistent there. Then the A inverse B is going to be the solution then. Okay? In theory, the combination of A inverse B will give me the answer. So what I need to do in any of these problems is I first identify A, B, and X. This you don't need to do. I was just showing you where the system comes from. So this is not really necessary. So you get A, B, X. Then you have to find A inverse. And it doesn't really matter to me how you do that. I'm going to go ahead and go to my calculator. Actually, you know what? It's probably faster. Might be faster not to go to the calculator. Let me just do the determinant real quick. See if I can get through this. Determinant of A is, go to this matrix, this one here. 1 times -3 is -3. And then subtract the other diagonal. 2 times 3 is 6. And that combination is -9. Then A inverse would be, remember we said it's 1 over the determinant multiplied by the matrix that occurs when you swap the A and the D. So you get -3 on top of 1 on the bottom, and then change the sign on each of these other two values. Okay. And if I were to distribute this -1/9 in, -1/9 times -3 is 1/3. Same thing on the other side. This would be a +2/9, and that would be -1/9. Alright, so there's our inverse matrix. If I take that inverse matrix, multiply it on the left times B, so I should go with 1/3, 1/3, 2/9, -1/9, multiplied by matrix B, which is 5, -8. We'll see how this goes. It's going to be a little bit messy with the fractions, so I'll give myself a little extra room here. First row, first column. 1/3 times 5 is 5/3. 1/3 times -8 is -8/3. Okay. Then second row, first column. 2/9 times 5 is 10/9. -1/9 times -8 is +8/9. And when I simplify these, 5 minus 8 is -3. 10 plus 8 is 18. And one final simplifying step. -3/3 is -1. And 18/9 is 2. And so here my answer is the ordered pair -1, 2, just like we had before. Right, -1, 2. It's a little bit more of a process than Kramer's rule or using our reduced row echelon form or any of those. But it is kind of a neat idea, utilizes the inverse matrix, and again gets us to the same result. Now you can do this with a system of 3 equations with 3 variables. You don't just have to do 2 equations and 2 variables. We could go even more than that if you wanted to. But this gives you another alternate way of solving a matrix or solving a system of equations.